from the stage master. No niin, kiitoksia kaikille paikalle saapuneille ja kiitoksia myös kaikille netin ääressä meitä kuunteleville. Mä olen Terra Cognitan kustantaja Juha Pietiläinen ja mulla on tässä vieraanani Ben Orlin, jonka kirja mulla on ollut kunnia suomentaa ja kustantaa. Ja Ben kertoo kohta itsestään. Me puhutaan tässä englanniksi, koska Ben on kotoisin Yhdysvalloista eikä osaa suomea tietenkään. Siksi käännämme hänen kirjansa. Ben, welcome to Finland and welcome to Rosebud.
Yeah, kiitos. Yeah, thank you so much. Yeah.
So, could you tell us a little bit about yourself? You're a math teacher, for one.
Yeah, that's right. The last 5 years or so, I've been more of a full-time writer, and so I feel, I've been doing less of actual being in the classroom with students teaching math, but that still feels very deep to my soul, and I think in the books, I think that probably comes through, that I still think of myself as a teacher. Like, what excites me most is getting other people excited about things and about the world.
Yeah, so what got you into doing these bad drawings and writing about mathematics then?
Yeah. So I finished university and started teaching and taught at a little tiny school. It was only about 150 students in California. I was there for 4 years. It was great because you really get to know the students very well in a building that small. Everybody doesn't have any choice but to get to know everybody. And at the time, I was still excited about writing, though. I'd done a lot of writing in college. And so I knew I wanted to write about math and felt like there was some missing element. And then it was in lessons, often I would need to illustrate an idea. You need to draw something to show students what an idea is. And I'm genuinely very bad at drawing. It's a legitimate weakness of mine. I really can't draw. There are other people who draw a similar style to mine because they're doing something deliberately minimalist. That is not me. I'm not trying to be minimalist. I'm not doing this on purpose. It's really the best I can do. Anyway, I would do that in class, and usually you get a laugh from students. They find it funny to see someone with such bad art. Somebody, the adult in the room who's ostensibly the expert who can't draw as well as the doodles they're doing. Yeah. Oh, sorry.
Closer to mine.
Can't even draw as well as the my drawings were worse than their doodles in the notebooks. And so, I found that when I started doing some writing online about math, started a blog, and it just seemed natural to illustrate it. And the illustrations were really quite amateurish, so I called it Math with Bad Drawings to sort of apologize in advance for how bad the illustrations are.
Right. So you also write about how the students kind of like found it, somehow you by humiliating yourself a little bit with the bad drawings, they also found the kind of like the courage to also fail. Because they found it. Yeah.
Yeah, I think that's right. I don't know if this resonates as much in Finland. I think the Finnish may have more of a patience for school as an institution, or perhaps more. Maybe there's a little less math phobia. I'm not really sure. I'm still getting a handle on how the Finns see the subject. Maybe it's exactly the same here as it is in the U.S.
I suppose it's universal.
Right. Yeah. So math phobia, I think, is certainly in the Anglophone world, and I suspect in a lot of the world, math just makes people anxious. People get nervous around math. There's a sense that to fail in math is somehow worse than failing in other subjects. That it says something more about your capacities, some kind of referendum on your intelligence. I don't know quite what it is, but people, they treat mathematical failure differently. And so as a teacher, one of the best things I can do for making them willing to kind of try things and make mistakes is just fail very publicly myself.
Right.
And so sometimes that's like I make a calculation error at the board. Maybe not ideal to be teaching them wrong mathematics. But the best way to fail publicly is to show them my drawings, where I did not do enough doodling as a kid. I really did not learn how to draw a dog. And I think in one of the cartoons in the second book, there's a chapter about a dog, and I show you all like 8 versions where I kept just trying to draw a simple stick figure dog, and it really took me about 8 tries before it was even recognizably a dog and not a weasel or just a very broken human.
Right. So, can you tell you've written 3 books, of which 2 have been translated. This was your first one, this Math with Bad Drawings. Can you tell me a little about, and our listeners a little bit, what they can find from this book?
Yeah, this one is, I think the subtitle in English that we did was something like Illuminating the Ideas That Shape Our Reality, which is very lofty language for what's actually a very down-to-earth book. It's about, there's chapters about all different places that math shows up in reality, so, by which I mean very concrete, earthy things. There's a chapter on lottery tickets. Is there a Finnish national lottery?
Yes,
Okay.
yes.
Is it very popular?
Quite.
Okay, yeah. I was surprised researching that chapter. I was surprised to see in the United States what the demographics are of lottery ticket buyers. I learned a lot writing it because I came in with some ideas I wanted to share about expected value and kind of the mathematics of lotteries, and wound up learning that Massachusetts, where I'm from, and it's sort of I think of it as like the Finland of the United States. It's like the educated, very civilized part of the U.S. But we're one of the biggest lottery ticket buyers, right. Which somewhat contrasted with my image of Massachusetts.
You're the most optimistic too.
That's right. Yeah, I guess that's it. We're very hopeful people in Massachusetts. So there was a chapter on lottery tickets. There's a chapter on why there aren't giants. It's sort of a matter of surface area and volume. There's chapters on, you know this as well as I do now, having translated it.
But keep telling these people down.
Right, that's right, yeah. Right. Well, I'm trying to think what else there is in there. There's a chapter on the Death Star, from Star Wars, and the idea of a spherical space station, and what would be the implications of having that geometry in space.
And the sheer size of it.
That's right, yeah. And then, so it's supposed to be about... ways that math shows up all across reality.
Right.
Yeah, ways that math infiltrates our daily lives and things we might care about, voting systems depending on math, and architecture and how that depends on simple mathematical ideas. So that one, is meant to be, I thought I wanted to lead people into some sort of hopefully surprising and interesting math, but every chapter I tried to start on the ground floor. So it's not, as we learned in chapter 7, this is how expected value is defined. Now we're going to define, nothing like that. It's much more, chapter 7 we did lottery tickets. Okay, now chapter 8 we're going to do sports.
Right.
So always starting from basics.
What I've somehow found charming about the book is like you start with the basics and then still you end up with some like pretty deep stuff, like talking about this kind of like there's this big problem with the reproducibility of the scientific results, for example in psychology, and you end up somewhere pretty in deep, let's say deep waters but still keep it somehow very earthy and down to earth.
Yeah, I hope so. Yeah, what I tried in every chapter was to make it a narrative about the ideas. And what I did was I skipped the equations and the calculations, which I think that was my secret weapon. There's a tendency among mathematicians and people who write about math to feel like we need to show every detail. Like somehow we've lied. If I haven't showed you exactly which steps you need to do this calculation, I'm being dishonest and I can't be trusted as a writer. But the books are short, you've only got so much space and you don't want to spend lots of time with equations, and a general reader doesn't necessarily want or need those equations. So as long as I feel like I'm being honest with the ideas, I tended to brush the equations under the rug, which let me tell, I think, different sorts of stories than a lot of books about math.
Right. So what about the other one? Change is the only constant in English. In Finnish, literally, Muutos, ainoa, vakio. What's this about then?
Yeah, this is about... in a word, calculus, which is a branch of math that gets a lot of attention in the United States. It's the math you take if you're an ambitious student planning to go to university. It's the math you take right at the end of high school. But in general, it's sort of seen as the first moment of modern math. It sort of developed in the late 1600s, Isaac Newton and Gottfried Leibniz, and it was taking these really ancient mysteries of change and flux, Zeno's paradox, and how is motion even possible if it's made up of infinite little steps. And suddenly it took those mysteries that had been around for centuries and turned them into almost clockwork, just this mechanical system of calculation. You get out your paper and your pen, and you can just crank through the mathematics and solve what had been incredible mysteries about how the planets move and about change over time. So it's a book about, some of those historical changes in how math came to be what it is today. And more than that, about how those ideas kind of affect everything, how they spread through philosophy and literature, and how those ideas are part of what it means to be a thinking human today.
Right. Also, what strikes me is that in this book, the first book, you talk about this really concrete stuff like buildings and lotteries, everyday stuff. And in this one, you start talking about happiness and power and wealth, you know, a bit more abstract or kind of like different kind of like aggregate stuff, you know, that.
Yeah, I was sort of following the writers who shaped that book. Right, we put together a stack of all these books back here behind the two books are ones that get referred to in that. Yeah,
second we'll book. talk about them a little later.
Specifics later. Yeah, but yeah, as I was sort of looking around researching that book, I was finding lots of writers. Jorge Luis Borges is an Argentine writer that I love from the 20th century, and Tolstoy. There were just lots of writers who had seen the ideas of calculus and been inspired to think different sorts of thoughts about what we would call philosophical ideas or romantic ideas, you know, thoughts about life and change during a person's lifetime, and about what it means to measure someone's happiness or to weigh the happiness of one person against another. And those might seem like questions where math would really not have much purchase, you know, and like not much of a foothold. Like clearly when it comes to lottery tickets, you should know some math. Right. Clearly when it comes to architecture, a little math is going to be useful. But yeah, the ones in this book, you sort of might think, well, what good is math for thinking about
happiness, for
example? Yeah, joy and sadness and civilization and democracy, right? This sort of big... fuzzy is the wrong word, but they're messier ideas. And it might seem like math has less of a role to play. But for me, those were really fun stories to explore, because I think there's an element that mathematical thinking can bring. You can't solve democracy the way you solve an equation, but math can give you some metaphors and ways of understanding democracy that have value.
Yeah, maybe we all have like some mental model of happiness that kind of like we can consider more in detail if we kind of like give it this mathematical form or try to even do it, and then kind of like find its weak spots or something.
Yeah, exactly. Yeah, like one thing that happened, there's conversations with my dad, I feel like this comes up a lot, is one tempting way to think about happiness is you have some amount of time on this planet, and the more time you spend doing stuff you like the more time you spend doing good, happy stuff, that makes you happier. Right. And there's some truth to that, but it turns out not to be quite right. And once you sort of frame it mathematically, you can get a handle of, say, okay, really what you're talking about is what a mathematician would call an integral. You're saying, take all the happiness from moment to moment, add it all up. Yeah. You need to be clever to add up all these infinite moments, and then you'll get some kind of final number for your happiness. Right. But then the psychology research is that, no, that really isn't how happiness works, that in fact one peak moment makes a bigger difference to people than lots of kind of nice moments. Yeah.
So, one more thing about this book before we dive into this.
Yeah, sorry, I'm already into the weeds on different theories of happiness. Yeah.
So, the name of the book is Change is the Only Constant, and calculus is basically it's differential and integral calculus, and so. The name of the book is a reference to the differential side. It's the math of change.
Yeah.
And can you talk about a little about that, these two sides of the calculus?
Sure, yeah. For those of us who are here in person, is calculus an evocative word for you? Do you think, yes, calculus, I have strong associations with that? Or is that like, okay, yeah, I think that's mostly the way calculus feels to most people. So broadly speaking, there's two halves to calculus. That don't at the beginning feel terribly related, but they wind up being two parts of a whole. The first is differential calculus, which is essentially the study of change, and in particular, change at a single moment. So as things change, really what change means is at one time you see this, and at a later time you see that, right? What it means for my car to be moving is that 1 minute it's here, the next minute it's there. Yeah.
Exactly.
Yeah.
Yes, exactly. Derivative is the change.
Yeah.
And integral is the other side of the calculus. So it's.
That's what calculus means.
Yes.
That's right. Yeah. That's what calculus would mean. Yeah.
In Finnish, differentiaali ja integraali laskenta, and in English it's differential and integral calculus, but they just dropped the differential and integral and left the calculus.
Yeah.
Oh, okay, yeah.
When I did it in college.
Right. Yeah. That's a different.
That's like not calculus anymore. That's more.
Yeah, I wouldn't tend to call that calculus. Yeah, calculus I think people would tend to use for the, specifically derivatives and integrals, sort of the, essentially like the solved problem of how do you differentiate and integrate elementary functions. And then actually differential equations would be seen as its own kind of separate branch. And there's lots of modern math grows out of calculus. So I'd say differential equations and analysis more broadly are all kind of the children of calculus.
What is specifically analysis? It's sort of like,
Yeah.
it's more like pure math?
Yeah, analysis is more like pure math, yeah. Yeah, it goes into, and these stories that I tried to fit in the book, and there's only so much space for some of them, but yeah, to a layperson, analysis is sort of the study of continuity, of tiny continuous changes. And yeah, Riemann sums. It has a reputation among mathematicians, and this is part of the tension in the book. The reputation of analysis among mathematicians is that it's very fussy, very technical. That it's it's not quite as bad as bookkeeping, but there's a lot of very nitpicky details you need to watch out for. And yet it's dealing with very fundamental natural things like motion and continuity. And so, yeah, a lot of what the book is about, and I think the history of these branches of math is about, is taking what seem like very natural, simple questions, like the nature of continuous motion, and coming up with a very mechanistic language for it. And yeah, that's sort of a weird process of... Yeah, exactly, yeah. Yeah, exactly. Yeah, like taking Zeno's paradox, and for an analyst, how do you think about Zeno's paradox? Is you work very carefully with sort of tiny quantities and imagine a little change in this and a little change in that, and you write these inequalities that let you kind of control everything.
There's a chapter or a passage about Zeno's paradox in the book. Yeah.
Right. Yeah. The book touches on Zeno's paradox. Yeah.
True. Yeah. So should we start? You use a lot of. You draw a lot of inspiration from literature, like you said, and there are lots of quotes and stuff like that. So, in the book, so I have a pile of books that you quote in the book or references in the book. And what I'm going to do now is I'm going to challenge you a bit. So I'm going to ask you. I have in my hand a book by Jorge Luis Borges, who's from Argentina, and you talked about him already. So this is a Finnish translation of his short stories. Very good translation actually by Matti Rossi from 60s. But how does what does this has to do with mathematics then?
Yeah, right. So I guess the game we'll play is right. You'll challenge me on each of these seemingly non-mathematical books.
Yeah, it's just fiction.
Right. Yeah. Right.
Fiction here.
Yeah. Borges is he's a writer I love, and I think if you survey around math departments, talk to math professors, his name comes up a lot. He's very much a favorite fiction writer among mathematicians. He was really fascinated by questions of the infinite, the nature of time. All across his books, you get the two kind of recurring images are mirrors and labyrinths. And so it's this idea of puzzles in which we can get lost, and a mirror being something that duplicates infinitely, that you put two mirrors facing each other and now you have a labyrinth, and a labyrinth that goes on forever. The story of his I talk about in the book, there are so many you could choose from Borges, but is one of my favorites called The Secret Miracle, which imagines a man on the eve of his execution. He was framed for a crime and is about to be killed. And the man is an author and was working on a play in verse, so a rhyming play, that he didn't get a chance to finish. And so as the firing squad is preparing to execute him, he prays and he says, "Oh, please, Lord, just give me one more year to finish this book." And right then, the bullets freeze in midair, and the raindrops stop falling. And there's this moment, and it's just going on, and he realizes that this one moment is now his chance to write his play. It's verse, so he can kind of go over it in his head. He can do it from memory. And so a year passes with zero time passing in reality, but an entire year in his head as he's thinking through these verses and taking advantage of this miracle. And then the story ends with he finishes his play, thinks to himself, good, thank you. And then the bullets resume their course and he's killed. But to me that was the idea that there's an infinitude in every moment, right? That somehow within each moment, if you can just
Zoom in.
Yeah, if you can zoom in, exactly. Yeah, and this is how the number line works in math. I'm working on a book that's about much more elementary math now, but I was just thinking about this idea, that you take the number line from 0 to 1, you carve it up into 10 pieces. We call those 0.1, 0.2, 0.3. Yeah. But you can keep carving up. We can go between 0.3 and 0.4. You can go to 0.33 and 0.34. And you can just keep zooming in. And in the real world, you can't do this, right? In the universe, you get down to about, 10 to the negative 35 meters or something like that. I think it's on that order of magnitude. And you're now at the smallest meaningful distance in some sense. Quantum physics.
Or a moment of time also.
Exactly,
Moment of time.
Yeah, the Planck length and the Planck time. Yeah, I think it's 10 to the negative 44 seconds, right? Yeah, exactly. Yeah, so there's something about our reality. Not that it's granular exactly. I don't know enough quantum mechanics to really quite explain it all. But that you get down to a point where it's the smallest meaningful unit. You can't really.
Also,
carve it up any further.
Kind of like, for me, it relates to the idea that in calculus, you kind of like zoom into the smallest possible moment, or to the infinitesimal sequence of time or moment of time, and that's kind of like the whole idea when you talk about velocity, for example.
Yeah, exactly. So what it means to look at the another one of Zeno's paradoxes. The famous one is, you can never cross a room because first you have to go halfway across, and then you have to go half of what's remaining. Now you're 3/4 of the way, but you still have to go half of what's remaining. And so there's infinite steps before you can reach the other side of the room. A slightly less famous paradox of Zeno's is that an arrow flying through the air can never actually move. So there can be no motion, because in one instant, in one moment, the arrow's not moving, right? If you look at a freeze frame, the arrow is just hanging there. And then time is made of moments. So in every moment in time, the arrow is not moving. So either the arrow must be jumping, like you've spliced together the wrong part of a movie and you've skipped a scene and it just jumps. That doesn't seem right. Or the arrow can never move. And what calculus doesn't quite solve this for real arrows, but it does solve it beautifully for by imagining a world where you can just keep zooming in and zooming in and zooming in, a world of continuity. Right. And continuity isn't quite how the real world works, as best we can tell, but it's a beautifully powerful idea.
Like good approximation.
Yeah, exactly. Yeah, it's simplified.
Exactly. So let's to another book.
Right, that was Borges, right.
That's Borges. In my hand, I have a Finnish translation here of Edwin Abbott's classic from 1884. It's slightly older, called Flatland in English, Tasomaa in Finnish. You have pretty much a whole chapter about this.
Yeah, that's right. Yeah, there's a chapter
from this book, in a way.
Yeah, that's right. Yeah, there's a chapter about Flatland. Yeah. This is a book I love. My wife is a mathematician, and when we were students before we got together, she recommended Flatland to me as this is the closest you will ever come to seeing the fourth dimension. Right, like we live in a three-dimensional universe, but if you want to picture a fourth dimension, this book is the closest you'll come to it. So it's a very peculiar little book. It's a Victorian satire. It was written in England, and it imagines this two-dimensional world. So it takes place on like a flat table. The main character is a square. His name is literally a square. I guess Arthur Square, Arnold Square, or something like that. So he lives this little two-dimensional existence. And the book begins by needing to explain what it would mean to live a two-dimensional existence. It's very weird. We're three-dimensional creatures, but we sort of see 2D, right? The back of our eye, the retina is two-dimensional. And so really, when I look out at the world, I'm sort of seeing like a 2D screen, and I have some clever ways I can infer, if I see something overlapping something else, I figure that's not a weird half-chair-shaped object back there. I figure one chair is in front of the other. So I have ways of inferring depth. If you were a two-dimensional creature, you would only see in one dimension. You'd be living on this flat table, and you would see essentially just a horizon. And that would be your entire field of vision. And you would have to infer from matters of shading or shining or light, what life was like. So anyway, the plot of the story comes going when our square is visited by a sphere passing through the plane. And of course, you can't see the whole sphere, so the sphere shows up, and he's like, oh, a circle. Wow, nice to meet you, circle. But then the circle starts changing sizes because
Going through the...
yeah, is the sort of imagine like the surface of water. Imagine a ball passing through water, and so the square lives right on the surface of a still lake, and the ball is passing through. And when it first enters the water, the square will perceive a small circle, and then as the ball passes through, that circle will grow. And then ultimately the ball will pass through to underwater, at which point, from the square's perspective, the circle has vanished. So this is a very strange creature. It's a size-changing circle. And it turns out that gives you a nice way of understanding spheres. And this is for mathematicians. If you want to find out the volume of a three-dimensional object, often this is what you do using calculus. You essentially dissect it into infinite layers. And by thinking of it as sort of adding together, a sphere, what is it? It's really infinite circles stacked one on top of another. And in the same way, a cube is an infinite stack of squares. And what's lovely about that is it gives you a little bit of an image of what it would mean to have another dimension. So if a three-dimensional object is an infinite stack of two-dimensional objects, then a four-dimensional object is an infinite stack of three-dimensional objects. So I still can't picture it because it's impossible to picture. But if a four-dimensional sphere could visit us, we would have the same experience as the square. It would show up, that we would see a little ball. As it passed through our universe, the ball would grow. These balls aren't really the object. They're really cross-sections of the object.
Three-dimensional
cross-sections, right. And then the same thing would happen as it passed through, the ball would shrink and then vanish. And at no point were we ever seeing the full four-dimensional object. At any moment, we were seeing just a three-dimensional slice of it.
Kind of like a three-dimensional shadow.
Exactly, yeah, like a shadow, or in this case, a cross-section. Yeah. I think my wife was right. That is the closest I've come to understanding what a four-dimensional object is. I still don't.
Jordan Ellenberg has in his new book Shape this joke about how to visualize a 14-dimensional space, and you think about really hard about this three-dimensional space, and then you say solemnly, 14.
That's right. Right, yeah. To understand a 14-dimensional space, right, yeah. You look at a picture of 3D and just say to yourself, say 14. Because that's all we can do. Right.
Yeah. So, next book. Let's take this. This is a little this is Leo Tolstoy's War and Peace.
Yeah. 2 heavy bricks in Finnish,
2 heavy bricks in English too.
Yeah.
What has Tolstoy to do with it? Mathematics.
Yeah. Well, first of all, having written books myself now, partly it's that Tolstoy's books are extraordinary, right? He's one of the great writers of fiction, but it's also just so long. How do you write that much text? I don't know. As someone who's now tried to write text for a living, it's almost impossible to imagine what it would be to write a brick like that. But in particular, what he was trying to do, the reason this is such a long book, of course, is it's war and peace, right? This was supposed to be a novel that captures the whole sweep of civilization and gives you an image of what human life in its full complexity and variety looks like. And late in the book, he actually introduces this kind of strange metaphor. First, he really rails at historians for a while. He says historians are complete idiots. And there's just sort of an essay kind of inserted in the middle of the text. But he says, the problem with historians is they think they know anything. They know nothing. They keep telling these stories where they'll say, why did this country go to war with that country? And it's because the king said this or because the prime minister did that. And to him, that's just an insane answer, right? Like, what is a war? A war is thousands or millions of people leaving their families, picking up weapons, traveling hundreds or thousands of miles to kill and to be killed. It's an insane process. How could that be, all of that activity, be attributed to, the vanity of one leader or another? And his answer is, to understand history, you can't look at great men, right? The great man theory of history is a non-starter for him. You need to take all the individual people, and even more than that, all their individual moments and impulses and desires and fears, and you need some kind of process for adding all of that up, taking this tremendous aggregate of every bit of human life. And he's actually very explicit. He says you need to take an integral, which is that's what you do in math. An integral is a sum of infinite infinitely small little things. And Tolstoy knew enough calculus that he said, we need calculus for history. We need somehow to take an integral of a nation or of a society. That's what we need to do.
Yeah, exactly. You need to find the infinitesimal
that's right.
first of the history and then add them up as an integral.
Yeah, exactly. And the infinitesimal will be something like a passing thought.
Right.
And somehow, or just a little behavioral tick, and somehow we need to take all of those and add all of those up, and that's history. That's what history really is.
I confess I hadn't read this book, but this really got me interested, and now I need to read this book. So.
Yeah, enjoy the next decade. I've not read every word. I've read parts. I've read enough to be able to write a little bit about his theory of history.
Okay, but anyway, let's see the next book. A little newer stuff. This is Thinking Fast and Slow by Daniel Kahneman. This also is a translation. Some of you might recognize the cover, but in Finnish. What about this?
Yeah. This is a book I love, and I guess it goes back to we were talking a little bit earlier about happiness, and so. Some early economists and philosophers around the same time. The one I quote in the book is Jevons. It was a British philosopher. Yeah. And so he was laying out a theory of, and again, knowing his calculus, he was drawing explicitly on the integral. He was saying basically, okay, happiness is an integral. How good you feel on a given day, like what is your level of joy on the day? What we do is we draw a graph. You say, okay, x-axis is time, going from midnight to midnight, and the y-axis is how happy you are, your emotion. So you start out when you're sleeping. I don't know, maybe you're having a bad dream, so it's low, and then you have a nicer dream, so it's high, and then you wake up and you're a little groggy, so it's low, and then you have a nice breakfast, so it's high, and you go the whole day like that, and you see how happy you are in every moment, and then you look at how much area is under the graph. And if it's really high the whole time, if you're really happy the whole time, that's a big area, that's good. And if it was low the whole time because you're unhappy, you're gonna have a small little area under the graph, and that's bad. And maybe you can have negative for when people are really unhappy or something like that. Which sounds, when you sort of say it like that, it sounds, at first, on the one hand, a little silly, because there's not a number for happiness, obviously. But on the other hand, almost tautological, almost obvious that, of course, that's what we mean when we talk about being happy. We mean being happy over time. And then where Kahneman comes in is to say that's actually wrong. It's just happiness just isn't an integral. He actually did it with pain rather than happiness. But there's a classic study that he talks about. There's a Nobel-winning psychologist, and it's a study where you take people's hands and you put them in uncomfortably cold water. And so if your hand is in there for a minute in, 32 degree Fahrenheit. Okay, so yeah, let's say it's a little higher. Say 2 degrees Celsius water. And so it's in there for a little while. It's uncomfortable. And then there's two groups of people. One group of people, you now heat the water up to 4 degrees Celsius. So it's still very uncomfortable. And you keep it for another 30 seconds. And the other group, you just take it out right away. So they have 1 minute of pain. The other group has 60 seconds of that pain, but then another 30 seconds of slightly weaker pain. And then you sort of ask people afterwards, how did you feel? And I think I don't remember the details, but I think they even had some people try both without telling them the time, and then say, okay, which one of those would you want to redo? And people really prefer the longer one. They prefer extra pain. And the reason is because the last part of the pain is a little weaker. So what's happening is when people remember their lives, you don't take an integral. You don't go clicking through minute by minute by minute, telling yourself, okay, well, that was pretty good. Okay, that was bad. You're not adding it up that way. He talks about peak end theory. So you remember the peak. You remember the extreme of the emotion. And you remember the end. And you remember the other stuff too, but disproportionately what matters is the extreme moment and whatever happened at the end. So giving somebody just a little bit of weaker pain at the end, their overall memory of the experience it wasn't quite as bad. Even though in total, thinking in terms of integrals, it sort of had to be worse. It was all the pain from before plus extra pain. And yet that's not quite right. And somehow the reason I like that as a sort of mathematical construct is pinning it down with numbers is what helps us to see somehow the how our own experience goes beyond numbers.
Right, but he also, Kahneman has also this other for me, really interesting way of quantifying emotions in his and Tversky's theory of loss aversion or model of loss aversion. It's also, there's this idea of drawing a curve of, emotion.
Yeah, that's right. Yeah, and that turns out to be a very useful model for understanding why people take the risks they do or don't want to take risks.
Right.
That's right in the first book.
Yeah,
right?
and it's, just to kind of like, it's just, it's not a bad idea to model emotions mathematically. It's just, that you have to be careful, and there might be some consequences in your model.
Yeah, that's right. Yeah, something I think a lot about. I was writing that second book that math is touching on all these things that feel very dear to us. And there's always something that feels a little bit violent about that. There's always something, I think in me and in a lot of people, that just rebels at the idea that we're going to try to put numbers on such rich and nuanced and inexpressible things as our experience of the world. And I think there's something true about that. There's always something lost when you try to put numbers on it. But there is something gained too. You can see patterns and sort of get to insights that you wouldn't have gotten without that kind of quantification.
Exactly. So, another book. Let's see. Here's Octavia Butler, A Parable of the Sower. What about this then?
Yeah.
This is science fiction, I think.
It is, yeah. It's science fiction written probably early 90s and set in a sort of discouragingly plausible sounding United States of America, probably set somewhere around the modern day. So it's sort of a society breaking down almost. And we have a main character who's navigating this world where now sort of nowhere is safe and government is ceasing to function. And this one, there's actually not a chapter in this book, but it gives the sort of opening page, the quote that begins the book. What's the word for that? Is there English? I don't know what I call it, like an epigraph or something at the front of the book. Is there a Finnish word for that phrase at the front of a book?
Motto, I think, would be.
Okay, all right, sure, yeah, okay. So it's like motto.
Yeah, motto.
Yeah, okay, yeah, exactly. Yeah. So I quote a paragraph or two of that. And what the main character is doing, she's trying to develop almost like a new religion to help her navigate this collapsed society. And for her, it's change. Another character asks her, so what is your God? And she says, well, change. And he says, change isn't a God. Change is just an idea. And she's like, yeah, what's wrong with that? Like, change is everywhere. Change is the one thing you can rely on. Everything is going to change.
Hence the name. Change is the only constant.
Hence change is the only constant, yeah.
Right. Okay, so let's have some poetry then. Rumi.
Yeah, Rumi, that's another one that gives so the second half of the book is on integrals, that idea of taking infinitely many, infinitely small things and adding them up into one whole. And Rumi has a beautiful line. It comes out different in different translations. So I don't know how the Finnish translation that you found does it.
There was no Finnish translation. I translated myself. I can look it up.
Great. Okay, yeah. Let's hear it. So yeah, go ahead.
Tässä on: kuule, oi pisara, antaudu vailla katumusta ja vaihdossa saat valtameren.
Okay, is that pretty close to a literal translation of the...
Pretty cool,
yeah. Yeah, so that's something, that's one of my favorite images when I'm trying to explain what an integral is you think about a lake. Where does a lake come from? A lake is rain. A lake is a lot of rain. That's what an ocean is, just a lot of rain. It's a lot of raindrops. And so the raindrop is playing the role of the infinitesimal, this, vanishingly small thing. But you get enough of them, and enough is effectively an infinite number, not in practice not really infinite, but almost beyond imagining how many there are. And you add them up and you get the whole. And yeah, I don't know, that feature of mathematics to me, it does have some poetic resonance.
Even mystic, like Rumi was a mystic.
Rumi, beautiful mystical writer.
Yeah. Okay, then let's see. This is new stuff. This is David Foster Wallace.
Right.
What about David Foster Wallace?
Yeah.
Infinite jest, päättymätön riemu in Finnish. It's amazing that this has been translated in Finnish.
Yeah, I guess that's a heroic work for that translation.
Yeah,
That's because Wallace is a difficult writer, right? Very interested in metafiction and kind of twists and self-reference, and he'll introduce abbreviations that he'll then use in strange ways. He was himself a very precocious math student, a very strong mathematician, also a very gifted young tennis player, and so he had this sense of kind of his promise in life was to do lots of mathematics. And then I think when he got to college, he found it kind of hard, but loved it, loved the language of mathematics, loved the ideas. So he actually wrote another book on infinity, sort of on the history of concepts of infinity. And there's this very weird passage in this where this is a novel with footnotes, which tells you what kind of, endnotes, tells you what kind of novel it is. It's got a couple hundred pages at the end, I think, of endnotes. And there's one part where he's describing a strange game that the characters are very bright teenagers, very smart teenagers, and they're playing this very weird game where they're simulating a war. And what they do to figure out how to, I don't know, how much ammunition you have or what military spending you're allowed to do in this war is they have this complicated formula. Go to EndNote, you go to page 1092. There's this EndNote that goes on for 3 pages explaining how it all has to do with the mean value theorem in calculus. And it's one of the weirdest moves for a major writer of fiction. And also, someone had told me that it was in there, so I went and read it. And I read it again, and I was like, okay, well, Wallace is really smart. I just must not be getting it. And then I read it again. I was like, no, that's just not what the mean value theorem says. The math is just wrong. The mean value theorem says, very simply, that like if you have, say a car is driving for an hour and it goes 60 kilometers, at some point during there, it must have been traveling exactly 60 kilometers an hour. Because, well, if it was always going slower, then it wouldn't have made it 60 kilometers. If it was going faster, then it would have gone more than 60 kilometers. And you can't go straight from slower than 60 kilometers to faster, so somewhere in the middle it must have been driving exactly 60 kilometers an hour. So all it tells you is there was a moment when that happened. It doesn't tell you when, it doesn't tell you exactly where, it doesn't tell you if there was 1 or 2 or 5 moments like that. It's what's called an existence theorem. And the way he uses it in the book, you would have to, it wouldn't be an existence theorem, he's trying to use it to like in a computation, which doesn't make any sense. And so, yeah, it's the only chapter in that book where the others are all me really admiring these writers for the way they used mathematics and that they saw connections. And this one is mostly me being puzzled about why did he parade this sort of useless and incorrect mathematics through this big, famous, hard-to-read novel. And I still don't know for sure. I think it's possible that he didn't quite understand how wrong he'd gotten it. But I think it's probably likelier that he was making some comment on his characters and maybe a little bit on himself, that there's something about mathematics where we're attracted to how cool and difficult sounding and obscure it can be. But if you dig, it's often just empty.
Right. There's this big, this style of literature called autofiction is now very popular in Finland and probably around the world too. But this is a very good example of the risks of reading a work of fiction as non-fiction.
Yeah, I suppose that's right. Yeah. Right. Yes. Do not trust it as a mathematics textbook.
Exactly. But but it's still weird because I think it would have been better if he'd gotten the math right.
I think so. Yeah. It's hard to know what he was. To me, it makes me think of some peculiarities of the American calculus curriculum, where we tend to teach some very abstract, these theorems that, they're very abstract, and it seems like very much a product of that education.
But it could also be just a jest,
It could be. It is right. The book is called Infinite Jest, so I probably should not take it too literally.
Okay, so there's let's go back to the classic, Aeneid by Virgil. So Vergilius in Finnish.
Yeah. Is this how widely read is Virgil in Finland? Would you say?
It has been translated twice.
Okay, that's
so
pretty good.
And there's some controversy about which translation one should read.
Sure. Okay. All right. Yeah. Right. As with anything. Yeah.
But here we have the English translation. What has this to do with your book?
Yeah, there was a chapter that was fun to write. Actually, one of the mathier chapters actually is the sort of quasi-mythic, quasi-historical figure of Dido, who's one of Virgil's, or not Virgil, one of Aeneas's love interests in the Aeneid. There's other texts that we have of stories of her sort of fleeing. Oh, I guess right. And I guess that's where he runs into her too, is in what we would later call Carthage. But on the Mediterranean coast of Africa, she had fled from her brother who was trying to kill her, and she lands on the coast and is told, "Okay, you want some land? You can have as much land as you can cover with an ox hide." So, like the skin of an ox, not all that much land. We're talking, enough for, I don't know, maybe a nice cooking fire and a pot. Not that much. And so what she does in the old text of this is that she apparently takes the ox hide and tears it into little strips and uses it to kind of fence off a little region. Which is funny because that's a very famous problem in mathematics called the isoperimetric problem, where you have a fixed perimeter, you've got a certain amount of rope you can use, or usually in the way we teach it to students, it's usually kind of straight stuff. It's like, you've got sticks. And so what's kind of the biggest rectangular path you can make, or the biggest rectangular area that you can fence off? And so I just walked through. It's a very classic calculus problem that happens to arise sort of naturally out of this funny mythic story.
Okay, so we have enough time for
right. Oh yeah, we can. I don't
maybe
keep
one.
rambling.
Sherlock Holmes.
Sure.
Is there something
Yeah.
about mathematics
Sherlock
here?
Holmes is another one actually who gets a little bit taken to task in the book for having gotten the math wrong. There's a passage in a story. So it's the story of a private school, sort of like a fancy boarding school in England, and a teacher vanishes, and I think maybe a student vanishes, and a bicycle is gone, and I don't know, probably a jewel or something. Anyway, they're trying to solve the problem, trying to find where this bicycle went. So they go up behind the school. They see some bicycle tracks, and Sherlock, the detective, says, "Aha! Now we know this was the bike tracks going away from the school." And Watson says, "Oh, but how can you tell? It's just bicycle tracks. How do you know which way they were going?" And Sherlock says, "You see here where the deeper wheel, right, the deeper rut, it must be from the back wheel, because that's where the weight rests, that has crossed over the front wheel. And so we can tell which direction it's going." And Watson goes, "Of course." And the funny thing about that is it's totally true, right? The back wheel is deeper, and the back wheel will cross over the front wheel. But that doesn't tell you which direction it's going. I show a picture in the book of like an example of what a bike path would look like, and you just can't tell. You don't know from that. That's not enough information. It just looks like squiggles. So it's one of these things you can get away with in a novel, not really explaining it. But it turns out there is a nice mathematical method for solving that, where you use tangent lines. So a little hard to explain that just orally.
Yeah, but tangent has something to do with the derivative, right?
Exactly. Yeah, tangent is sort of like instantaneous motion. So when you think about if I had a like a ball on a string and we're swinging it around my head, and then the string breaks, the ball doesn't keep going in a spiral. The ball just flies off in whatever direction it was facing, sort of at that moment, whatever direction it was moving, and so that sort of it flies off the tangent line to the curve that I was tracing out by swinging it around.
Right, and you can calculate the direction by calculating the derivative and...
yeah, exactly, yeah.
Yeah. But there's also this, I kind of like the idea that the nemesis of Sherlock Holmes is the mathematician Moriarty, Professor Moriarty.
Yeah, that's right. Yeah, given that I was writing about Sherlock Holmes, right, I didn't come into it to write about Moriarty, but given that it was a math book and I'm writing about Sherlock Holmes, it seemed, sort of necessary to touch on the idea that the kind of the evil image of Sherlock Holmes, right, what is his exact opposite, the villain version?
Nemesis.
Yeah, his nemesis is a mathematician who's, published papers on the trajectory of asteroids. Right. That's what he's famous for. And in this case, actually, his nemesis would have gotten the question right, I think. Sherlock Holmes just makes it up and happens to guess right which direction the bike is going, but Moriarty would have known better.
Right. Okay, I think we're pretty much done. We've talked about almost an hour now, and I think we have, Or do you want to, we still have one book, Mark Twain.
Oh, Twain, sure, yeah. Oh, yeah.
You have a Twain reference in the book too.
I do like Twain. Yeah, that's a passage that I first learned about from Jordan Ellenberg, who wrote another nice book that you guys have translated into Finnish. But so it's a passage where Twain. I'm not going to be able to quote it from memory, but the gist of it is. He notes that what happens with the Mississippi River sometimes, right? It's a long, winding, old river, and so you get these meanders, right, where it sort of carves out a circle. or an almost circular motion. And what will occasionally happen is the water will jump the gap. So the river goes around this long curve. And sometimes, during a storm, it floods a little bit, and it carves out a new path that cuts off that curve. And you get what's called an oxbow lake. You get kind of a lake formed off to the side, a little pond, and then the river shortens itself. And so he makes the point that we can track how often this has happened. You look over a course of 100 years, and the Mississippi River has gotten, a couple hundred miles short, not 100 miles, but a few dozen miles shorter. And he says, and here's where we can extrapolate forward into the future. The Mississippi River has gotten 50 miles shorter over the last 50 years. So these aren't the exact numbers, but something like this.
We can plot it in the...
Exactly, we can plot this. And so in another 800 years, the Mississippi River will be 1.5 miles long. And in fact, these two parts of the United States that are currently 1,000 miles apart will, be one town with sharing the same mayor. And that's how it'll be. And so it's a joke about... to a mathematician, linear thinking, linearity, right? Assuming that because we see a pattern going on for a little bit, it's going to continue forever. And to a mathematician, everything is linear if you look close enough. What happens is any curve that's changing, right? So maybe the river is getting a little shorter, but then actually it's getting longer, and then it's getting a little shorter again. If you zoom in close enough on any part of that curve, it looks like a straight line, right? Same as like the Earth is not actually flat, but it sure looks like it because we're very zoomed in on the Earth. I'm looking, when I live on the Earth, I just live on a tiny, tiny little part. And so that's sort of the calculus idea behind it. The thing I liked was when I went back and read through the chapter where Twain makes that claim, he actually then makes the same mistake about 5 pages later, where he's talking about sediment that gets deposited at the end of the river, and he says, from this we can figure out how old the river is, or I forget exactly what he deduces. He figures out how long the river was 1,000 years ago or something, or 10,000 years ago. And the thing is, he gets it totally wrong because it's true that if the sediment had been deposited at the rate he thought, sure, then he would be right. But he wasn't taking into account the ice age or the fact that the curve is more complicated when you go deeper into the past. So it's sort of funny that Twain, brilliant guy, but he makes fun of this error and then makes the same mistake. Yeah, 5 pages later. Yeah.
Okay, I think we talked about the books. Does the audience have any questions? Oh, okay. I'll take you.
I think there's a question over there.
Yeah.
Oh, yeah.
Just a second.
Sure.
I'll give you the microphone.
Oh, sure, yeah. So the folks on watching the streaming can hear.
So thank you for inspiring thoughts. Juha and Ben, you are both math teachers.
Yeah.
So do you think that telling these stories also inspires teenagers to learn the hard mathematics on lessons and so on? Do you use it a lot?
Yeah, I think... Well, I'm curious to hear your thoughts, Juha. I think inspiration in education, it's easy to get carried away. I know sometimes as a teacher I do, or we do as teachers, to think that it's sort of all about inspiration. And it's not all about inspiration. There are skills that students need to learn. But it's a really nice ingredient to have. Inspiration, maybe, right, sometimes I compare it to a spice. It's what makes the whole thing taste good. It's not, you don't put in 2 cups of cinnamon, you put in a teaspoon of cinnamon, but that the one's being a very vital ingredient. But maybe inspiration is more like the baking powder, the thing that the yeast, the thing that makes it rise. Because I think inspiration's a pretty vital part of education. What you can't do without is motivation, right? Every student needs to be motivated to learn because there are infinite ways to not do something, and if a student doesn't want to do it, they will find a way not to do it. So there's lots of ways to draw motivation. Some draw motivation from pressure from parents is one place you can get motivation, or being really driven to pursue a career, or just I think for a lot of students, I think this is the way I was, just kind of wanting to be a kid who gets approval and good grades, and I don't think I was thinking that hard about what I was going to do in the future, or why education mattered. I just it's like I wanted A's because it feels good to get A's and think the teacher thinks I'm a good student. Inspiration can be, in some ways is a nicer source of motivation than some of those things. To have a student think, just be filled with curiosity and excitement about what the subject can do. That can be a very powerful rising agent, I guess.
Well, thanks, Ben. What I think, I would like to add to what you said is that learning anything is something that a person must do themselves. You know, a teacher can't make anyone learn. Teacher can help them learn something, but learning is a process in your head. So you have to learn mathematics, you have to think it through, you have to actually learn how to do it. And it can be very inspiring if it's, you know, sometimes it's easy and it's fun when you get you know, ahead, and it's great. But then there are moments when you're stuck, and I think inspiration kicks in those moments. You know, you have to have this kind of like idea. Why am I doing this again? Why is this valuable? Why should I care? You know, and I think this is one of the reasons. So it's kind of like when you have this idea of mathematics as something that's deeply part of what we do and what's our history and about literature and being human. Like, what are there any other animals that do mathematics? I don't know, but probably not.
Yeah, I think nothing we really call mathematics. Nobody sits down and gets coffee
starts doing algebra. No.
Yeah.
So basically, that's I think inspiration is important part of that. And teacher, when I was a teacher, I used to tell stories. At least sometimes, you know, I tell them about, you know, the different dimensions, the fourth dimension, to give them an idea. Didn't go into the details, but, you know, kind of like give them idea that, you know, they might want, at some point they have this kind of like idea that I'd really like to understand the maths of fourth dimension, and they would, you know, end up going to the university lecture to find it out or something like that.
Yeah. So I think inspiration, you know, as part of the various ways that we try to motivate students to care about the material. Yeah, there's some things that kind of inspiration can do that other kinds of motivation can't. Doesn't mean to say that every student who succeeds has to be deeply inspired. And it's also not to say that, you know, you want to devote 3 hours every week to inspiration time. You know, in some ways it happens better if it's a little spontaneous. Students love to be distracted from, you know, if they can get the teacher off the lesson, that is like such a delight.
It's a win.
And a triumph for them. So in some ways as a teacher, I think, you know, I think I did this when I taught, I'm not teaching calculus right now, I'm teaching them statistics. But I would have those stories in my back pocket, and you could tell when the energy was a little low in the room. And it'd be like, oh, did I ever tell you about the function that's all right angles? Just every single point on it is a right angle. It's like, what does that mean? It's like, oh yeah, you know how you can draw a function where one point is a right angle, goes up and then down, you know, kind of has a sharp corner. And there's a function that's all sharp corners. It's like, what are you talking about? What does that mean? And you don't learn about that until you take a real analysis course in college. But those little provocations, I think, can be a valuable part of an education.
Okay, anything else? If I'll give you the microphone, there are people listening online.
So can you explain, like, what was the Wallace thing that he did wrong in his book?
What did he do? Yeah, so what he does, I'm trying to remember. It's something like he is defining, right, in the game you're playing as countries. It's some weird game played on a tennis court where you're kind of throwing tennis balls, and the tennis balls are bombs, all very militaristic. And so he gives a definition of, okay, so there's this statistic, you're going to measure the ratio of this ratio to that ratio. It's like GDP per capita compared to military spending per capita, something like that. It's like a ratio that doesn't really make that much sense. And then he says, and we can find that ratio using the mean value theorem. But it doesn't.
And he takes the average.
Yeah, right. It doesn't. Yeah, it's not. I mean, you can take an average. You don't need a fancy theorem from calculus to take an average. If you want to take an average, go ahead, add up your data, divide by the size of the data set. You've got an average. So you don't need to invoke the mean value theorem. In fact, what I talk about a little bit in the book, the mean value theorem. You know, if you said the mean value theorem to one of the people who developed calculus early on, you go to Newton or Leibniz or the Bernoullis, and you describe it, they'd go, "What are you talking about? Why do you need that?" Like, yeah, I see what you're saying. It's true. But it's totally unnecessary. Why are you talking about that? Because it was only in the 1800s, particularly with the rise of Fourier analysis, which is now used in signal processing, that they started caring a lot about why exactly does calculus work? because they were running into some infinite sums that seemed to diverge and some that seemed to converge, but maybe not in quite the right way. It was like these sort of very fussy questions of exactly what is a valid sum and what is not a valid sum were suddenly very important for Fourier analysis. And so this calculus that previously they'd sort of understood this all works, and it just hadn't been the top priority to go back and put it all on sort of firm logical foundations. Everyone sort of knew that it worked and knew that you could go back and do something kind of like what Archimedes did, and you would sort of be able to prove it. It would be very slow and hard to write down. But as they got into the 19th century, they just needed more rigor than that. And so that's where these theorems like the mean value theorem came down, is if you want to start from very simple assumptions and prove everything we know about calculus in this rigorous analytic way, then you need to sort of the things like the intermediate value theorem and the mean value theorem, which are very obvious statements, if you unpack them, became very important stepping stones in that kind of proof. But the way David Foster Wallace is using it, it's like that's not what he's doing. He's just trying to do a calculation, and you don't need it for a calculation. So in some ways, it's an error that's somewhat typical of a certain kind of math education, where we present math as though everyone is a 19th century analyst who really cares about whether we can rigorously prove all these statements. But that's just not, like, even 18th century mathematicians didn't care about that. It's a little funny. It's like this very specific historical moment that really drives a lot of math education. And so it's not just Wallace making that error. I think it's a somewhat typical, well, that specific error is just Wallace. But using that kind of math when it's not needed is a somewhat typical error of a certain kind of mathematician.
Thanks, Ben.
Yeah.
I think we can wrap it up here. Ben will be signing his books by the cashier there, and you can buy. There is also a small bundle offer, pinkka tarjous, for the both books, and so I hope that I will see you guys there in a couple of minutes. Thank you very much for listening.
Yeah, thank you all. Kiitos.
Thank you also everyone online for listening. Appreciate it.